Good afternoon, everybody. Thanks for attending, especially Max. So you're welcome to start the presentation, Max. I think it's already started the recording. Thanks, Max.
Okay, thank you. So hello, everyone. Thanks for joining this meeting. So first of all, I will introduce myself. So I'm Maxime Bomme, based in France. I've been the Presales Engineer for the CFD solution at HEXAGON for the last 10 years. And I wanted to take the occasion today to introduce you to this solution and to explain you what we mean by calling it a pragmatic CFD tool. So during this presentation, I will start with a brief definition of what we are talking about and what we mean by CFD, by pragmatism and so on. And then I will try to illustrate for different industries what we can bring specifically for this kind of applications. During this presentation, so I don't remember, but it's in the list here. I will also show you the software itself, because I think it's important when we say that we are pragmatic to show you what we mean by setting up a simulation with our tool. So here we go. So first of all, what are we talking about? CFD, computational fluid dynamics. So we are talking here about the Navier-Stokes equations that you can see here. Usually that's not the best memory you can have from your schooling. So the good point with CFD simulation tool is that all the boring tasks with solving all equations and so on will be directly handled by the software. So that's a good point for you, because it means that you can focus on what really matters. What really matters is to get results and then to be able to take decision out of them. So when dealing CFD simulation, you will face several challenges. Among them, of course, accuracy, because there is no point in running a simulation if you cannot expect an accuracy of the result in the end. You will also get some challenge about the time to solution, because yes, you want to do CFD simulation, but if we tell you that it takes 6 months to get valuable results, maybe you will change your strategy. And the last challenge here, it's about dirty CAD, because you know what it is. I guess that's the same for all different kind of simulations, but there is the dream world, let's say, with beautiful models that you can directly take and process with your simulation solution. And there is a real world with dirty CAD assembly that you have to deal with. And actually, this is what we are facing here. When talking with people handling CFD simulation, we realize that they spend the majority of their time about cleaning some dirty CAD. And definitely that's not where your value should be as a CFD user. Your value is definitely not about simplifying some geometries and cleaning some dirty stuff in there. So more than words, I just want to show you what we mean here by pragmatism, linked to that specific challenge about dealing with dirty CAD. This example, so it's an electric cabinet with different racks of battery packs. This assembly is made of 5,000 parts. You have a front door with some fans, as you can see here. And the point is to push some fresh air across the different racks to cool the cabinet down. 5,000 parts. If you want to tackle that with traditional CFD approach, with closed volume, clean geometry and so on, of course, maybe the best start would be to start with producing another CAD simplified to represent your model. But you are spending time to make approximation. So definitely that's not the best deal. Here, with our solution, we have been able to process this 5,000 parts assembly within half a day. I mean, we get the CAD, we import it in the solution, we mesh it, we run the simulation, and then we get the results in half a day. So this is what we are talking about when we say we are dealing with a pragmatic tool here. We're providing a pragmatic tool. Of course, it's not magic. It's about the right tool that you use for the right purpose. Here, when we are dealing with dirty geometries, the key point is about the meshing techniques that you will be using. Of course, in our solution, we have a wide portfolio of different meshing techniques. We can use polyhedral mesh, so the standard approach. You get CAD geometries, then you get closed volume, and you fulfill that with mesh elements. So it could be very interesting in some application, depending on what you want to get in the end. For example, if you are running a validation simulation at the end of the project, your project, maybe that's the best approach. We can also use spatial hexagonal, meaning that you will use polyhedral mesh near from the walls and the shapes. And then in the far field, you will use hexacells, limiting the number of surfaces and speeding up the calculation. You can also use structural Cartesian mesh. It means that your geometry will be turned into hexacells, bricks, basically, so that you can directly process to that. And we also have in between here what we call the voxel fitting mesh. Voxel fitting mesh, you import the geometry, and then you specify the software, what is the level of detail that you want to be kept after meshing process locally for each single part. So with all these meshing techniques, we are able to save a lot of time in terms of CAD preparation and model preparation. But preparing the model is not the only point where you can also save some time. Here, we are talking about the solving. All solvers are designed to make the best of the hardware that you have at your disposal. We have been running some simulation, can be on the cloud computing. Here in Japan, we have also run some tests on Fugaku, so it's a supercomputer there. And as you can see, several hundreds of thousand cores have been used with our simulation tool. And as you can see here on the efficiency curves, yes, the software is designed and the solver is designed to make the best of your hardware, whatever it is. And then you get your results. But as I said, the end of the day is not to get a mesh, it's not to get the result themselves, it's to take decision based on your results. So here again, with the results, we are also able to boost your productivity in terms of CFD usage. For example, here on the left, you have fancy pictures. So yes, we can do fancy stuff. We can do beautiful images, photorealistic rendering, and so on and so on. But we can also bring you here to the next level with a better understanding of your result. I will come back to that in a minute, but we give you, again, another understanding of what's happening inside your system. So, as I said, CFD, that's a wide topic. So there are multitudes of applications that can be addressed here. So I will try to show you here for a few of them what we can bring in addition to that. First of them, electronics. Electronics, it can be at different level. Can be on the package level, can be on the system level, to be sure that you will be using the best cooling strategy. Will it be with fans? Will it be with cooling water jacket, and so on? So more than word here again, this is an assembly, and we will use our Cartesian mesh. So this assembly, it's made of few hundred parts. There is everything that you could put in a nightmare of CFD user. As you can see here, you have intersection between parts, because, for example, there has been no Boolean between the pins and the PCB. You have bolts, you have marks, you have nuts. Everything could be in intersection with the fillet, especially. You have square pins in round holes. So, as I said, on a CFD user perspective, that's a nightmare because you know that you will have to prepare the geometry. With our solution, a global edge length, a level of detail we want to be kept after meshing process. We are talking about 12 million cells. And here what you are seeing, it's a live capture video. It's not accelerated by any post-treatment of the video and so on. This is a live mesh. 12 million cells within 5 seconds. On the CAD that has not been prepared in advance. So this is what we are talking about here in terms of pragmatism. So that's to be able to handle complex geometries. But in electronics, we are also dealing with ECAD, for example, geometries that are coming from the electronic world. We are able to import them directly. For the components behavior, because these guys will be dissipating some heat, we want to catch the thermal behavior of the component. We are not interested about what is inside the component. We are interested about the way it will thermally behave. So we can represent them with very smart modelization. In the same way, if we are dealing with fans, with heat pipes, with Peltier device or other device, we have very smart ways to represent them, not to take into account every single detail of these kind of devices, but to catch their macro effect on the system. And there is also a next level with BCI-ROM. If you want to put some machine learning intelligence here in your simulation, we can also embed some reduced order model within this kind of simulations. About results, I've been touching that a little bit a few minutes before, but here, let's go into the detail. You are dealing with electronic system that will dissipate some heat. But here you get the result with the fancy animation, the CAD and so on. Okay. But we can bring you here to the next level with this kind of analytical results. With this kind of results, we can show you here where the heat is going inside your system. With this kind of visualization, you will be able to take some very key decision for your design. Few examples of them here. For example, for heatsink, you put some big heatsink in your system, you will be able to check if it's working on its full capacity, or maybe just half of the heatsink is working. So why not just reducing the size of it? If the radiation is your best ally to extract the heat out of your system, why wasting time in designing heatsink shapes and so on? Focus on radiation. So it will give you this level of understanding of what's happening inside your system, to give you some hints about what is the best modification design that can solve your problems. Here an example, these guys are designing some scanning devices. And before using our simulation tool, they used to spend 2 to 3 weeks between the moment they receive the CAD and then they get their first result, 2 to 3 weeks. By adopting our simulation tool, they reduced it to 2 to 3 days. X7 time folding for the CAD to result. This is what we call pragmatism. You are not here to spend weeks and days and weeks to prepare the geometry. You are here to get a result and then to take decision. This is pragmatism. Another application, automotive. For automotive, of course, this is again very wide in terms of application. If we are looking at the trend now in automotive electrification, yes, of course, we can do external aerodynamism. Yes, you will be able to get the car with the beautiful arrows around that and so on. If you are not able to do that, you cannot really say that you are doing some CFD. So yes, aerodynamism is still important for cars. We can also deal with electric motor simulation to be sure that the motor is working in the best condition in terms of durability and efficiency. We can also deal with the power electronics, for example, inverters that are just aside these motors. We can deal with the thermal management, because it can sound weird, but we are not talking about combustion engine here. But of course, we can do some under-the-hood simulation with traditional and conventional engines. But here, with electric cars, the thermal management is even more crucial, because these guys, the batteries, are very sensitive for the temperature. Can be for efficiency, but can be also for security. By the way, we have some very smart modelization for battery, as I said, for security and for efficiency. But all these new techniques with electric motors and batteries, they are also very sensitive to temperature. We can also deal with, for example, lighting systems, to be sure that everything will be kept under control, no condensation, these kind of things. And we can do also some comfort analysis within the vehicle. Here, just an example of underhood simulation. I was just talking about that. But when you consider this kind of complexity regarding the CAD geometry, of course, using the right meshing techniques will save you not only hours or days, but weeks. We have been in touch with guys struggling for weeks about this level of complexity in their design. By adopting our solution, again, reduced to 1 day. 1 day to be able to mesh all this complexity. That's a game changer in terms of preparation for simulation model. Here, just another example from a customer, so designing some battery packs. So here, this pack contains something like 300 cells, and using our battery modelization, they have been able, and our meshing techniques as well, they have been again able to reduce. Previously, they were spending 3 weeks to make this thermal simulation on the battery pack, reduced to half a day with our solution. Another application, HVAC and architecture. When I say architecture, it's not just civil architecture, it can be also, for example, the way to design a plant. Here, for architecture, different challenges that we can have, but this is the kind of things that we can touch with our solution as well. So, for example, directly importing the geometries out of architecture solutions. We are talking about Autodesk Revit, ArchiCAD. So definitely they are not using CATIA or SolidWorks to design the buildings. So we are also able to import directly their geometries. And again, we don't ask them to refine the geometry because there is nothing more dirty than a building geometry. I don't know if you already have a look at this, but this is really dirty. So that's a good point. You don't have to waste your time on that. We also have some nice modelization if we are talking about AC units, to quantify what is the amount of AC unit that we should place in the building or in the room. Where should we place them to get something very efficient and to control the temperature? We can also link to some architecture specifics here with the solar radiation database HVAC. It means that in the software directly you can tell where you are on Earth at the time of the day, at the time in the year, so that it will automatically pick the correct amount of solar radiation to be taken into account. I'm based in France. If I do a simulation for a French building, definitely the solar radiation to consider here will be different than one in Pretoria. So, as you may, so I have experienced it in the past. Your solar radiation is a little more intense. So, of course, you need to consider that as well to remain relevant. In terms of physics, what we can deal with this kind of simulation for buildings, we can deal with, of course, the wind speed. We can deal with the temperature, the humidity, the thermal comfort. That is nothing more than a combination of all the different results. But for example, we can directly output some PMV, PPD, or ICT, or wet bulb temperature. So some standards in terms of thermal comfort, we can directly get them as a result. We can deal with solar radiation. I touched on that. We can deal as well with free surface. For example, if you are working with fountains or active cooling system, we can deal with that. And particle tracking if you are looking for pollutants. So here, just an example about data server room. So here we have some AC units. We have the racks of servers. And here we can check what is the air behavior inside the server room. Is it under control? Why did we put 4 AC units? Because maybe it was the best solution here. We can not only have a look on the airspeed, but also on the temperature. Another example here with elevator shaft. So in this specific example, actually the geometry they provided was the full building geometry. So we just isolated here the elevator shaft, but the point was on one side to predict what would be the acoustic, the noise generation from the elevator, but also the thermal ambience here in the elevator shaft, because you have to be sure that the temperature is remain in a reasonable range to make sure that all the machinery will be working in good condition. So do you put AC unit? Do you use natural ventilation, depending on the solar intensity and so on? So a lot of different problematics that we have been able to solve here with our solution. Another customer here based in France, so we know them pretty well here. They are using our simulation tool to design clean room. So it's very strict in terms of control of atmosphere. And what you see here on the screen, not only they do the simulation, but they go on site and they overlay simulation to reality through an iPad. So this is also something that you can touch, augmented reality. We can do virtual reality, but also augmented reality. With the iPad, you will just, through the camera of your iPad, overlay simulation to reality. Few features that we are able to address here: daylight simulation. We can deal with solar radiation, so we can deal as well with daylight simulation. We can deal with pollution on a district level, as you can see here. We can deal with tsunami hazard. So the solution is Japanese. So unfortunately for them, they are more exposed to this kind of hazard here. Can be also here for energy purpose. It was done in India here. It was to anticipate what would be the impact of putting and building here a dam in this groove of a mountain, to be sure how it's behaving, retaining the water, and what comes after. When the dam is not enough, what will be the impact on the water flow? Another application, turbomachinery. The more it moves, the better it is for us, because actually with our meshing techniques, we are able to go where competitors cannot follow us. Not only about moving parts, but interpenetration of the motion. If you look here about a gear pump, here the tooth will be interpenetrating their area, and we are able, with very smart meshing techniques here, we are able to catch this very efficiently and to save a very huge amount of time in terms of calculation time. So of course, our customers are constantly comparing simulation results and what they get from experiments. Time for me to show you the software. So let's start with a blank sheet. So here we start with the kicker. We choose to call the pre-treatment, to follow here the solver monitoring, to launch for post-treatment. We also have access to all the documentation of the software. If you are keen, for example, on equations and so on, you will get your bedtime reading. That's not what I prefer, so I will directly focus on the software itself. So here, pre-treatment. I start from a blank sheet. I will show you an example of a drone model. Okay, so where do we want to store the files? Then next step, about importing the geometry itself. So in my case, as I said, I will take just a drone model. It's here. Okay. In terms of CAD geometry that we can import, as you may have guessed, we are not trying to stop you or to limit you here in terms of possibilities. So not only we can use neutral files such as Parasol, step file, but also native files. If you are using CATIA, if you are using SolidWorks, Creo, NX, and so on, you can directly use your geometry. So in that example, I will take this model. So it's a drone with its propeller. So as always, in the CAD geometry, you have the solid parts. That's good for structure calculation. For CFD, we are more interested about the surrounding. So why not creating the volume that will surround this geometry? So for that, we can create a kind of plenum. Okay, so it will be a cylinder oriented in the X direction. And then we will tweak a little bit the dimensions. So let's pretend for a minute that this volume will be enough. Okay, so then we get our volume of air. How to consider the rotation of the propeller? So for that, what we will do, we will also rely on a smart way of meshing techniques. It means that around the propeller, we will consider some air in motion. And then the rest of the domain will be considered as static. And the solver will directly make the link between the moving area and the static ones. So again, we just select here the propeller and we ask to create a specific volume around this propeller. So again, I will tweak a little bit the dimension. Something like this, okay? So we have this volume of area to be considered around the propeller, in which the propeller will rotate, okay? And then I will tell the software, okay, I will deal with this, what we call discontinuous mesh, moving area and static area. And for this discontinuous mesh, I will just tell him, this guy will be in motion. Okay, so he's just telling me here, I create one group for moving parts, one group for static parts. So of course, here the propeller will be moving, and that's it. At this point, I can also choose what kind of mesh do I want to use. Polyhedral mesh, traditional approach, or voxel fitting mesh if I'm facing some dirty CAD. In my case, it's clean enough, so I will just go here and proceed.
Sorry, Mike.
Yeah.
I made a mistake. I share my screen, so we cannot see your screen anymore.
Tell me when it's back.
You're back, yes, thanks, Max.
Okay, perfect. So as I said here, we will just look if the CAD is clean enough or not to get a mesh without any problem. So with that, we will just use, so we can enter different parameters depending if you are looking for accuracy or some rough estimation or simulation. And we will ask here the software, is my CAD clean enough to get close volume and to be able to mesh it? If there were some problems, it will directly point me where are the problems. In my case here, it's clear enough. Okay, now I can proceed, because there is nothing more frustrating than setting up the simulation and then realize that you have a problem for the mesh. So once I have my closed volume, then the next part, it's about assigning material properties for the different volume. Here in an external aero simulation, it's quite basic because here I will just consider the external plenum. I will consider the moving area around the propeller, and I will just tell him, we will consider fluid, can be compressible, incompressible. Just make it simple here. We consider air around the drone itself, and the different part of the drone will be just considered as obstacle. No airflow in that. And that's it. Now I can consider, I can specify regions. So what are regions? Regions are just one or a group of surface that we want to identify. Can be for multiple purposes. For example, here in that case, if I want to assign a velocity for the air, I can directly here recognize this front area. I just select the surface and then give it a name. This is the rear area. The side. Okay, and why not as well identifying the drone itself? So here, one group selection for the drone. We can do the same for the propeller, for example, but anyway, you get the drift here. So I just identified different areas, okay? From here, then I will set up the simulation. What do we want to solve, sorry. So here, so no worries, I won't explain in detail all of the panels, but I just want to show you here the main ones. The first one, analysis type. This is where you can add or remove some physics. Regarding the flow calculation, yes, I want to solve the flow. This is my main purpose. If I want to go in detail, what will be the way to deal with turbulence? What will be the turbulence model that I want to use? What is the kind of solver? Is it coupled, uncoupled, and so on? If you are not familiar with CFD, don't worry. SimTech guys are here as well to support you about the best usage of the software. So don't worry, we won't ask you. It doesn't take a PhD in CFD to be able to use our CFD solution. Why? Because it doesn't take a CFD PhD to get CFD problems. So again, we want to remain in the pragmatic world. So regarding the physics, we want to catch the flow behavior. Maybe we are not interested about the heat, so you just need to check or uncheck. Regarding the rotation and motion, if you remember, we want to consider the motion of the propeller. So since we have already specified the software, it's already checked. Now let's move to the basic settings. Are we dealing with a static simulation or steady simulation? Because there will be motion, but maybe we are just looking at the equilibrium. Or maybe we can also go to a transient simulation, meaning that we will follow along the time what will be the influence of the time regarding the different parameters. So here, just make it simple. Do we want to consider gravity? Okay. Now let's talk about boundary condition. If you remember, I have registered some regions. So one of the purposes of the region is to assign boundary condition. Here I have my front region. I can tell the software, we want to consider a velocity for the air. Okay, what is the velocity? What is the unit system that you are working in? And just assign this condition to a specific region. For the rear, maybe we would just set a reference pressure. Okay. For the sides, since it's a virtual plenum, here, if you remember this plenum, this is my decision to make this side. So I don't want him to calculate any pressure loss here inside this tube. I just want to consider something virtual. So I will just tell him, okay, on the side, don't consider anything. It's just virtual. Okay. Now let's talk about the motion of the propeller. So here, if I zoom a little bit, we have this propeller, it will be in motion. So we just go to moving elements. And if you remember here in the tree, he has already created a moving area. So just select the moving area, what will be in motion, can be several of them, but in that case, it's just one. And you just create a motion condition. What is it? Is it a rotation? Is it a translation? A stretch? Is it a 6 degree of freedom? So depending on what you want to get, just pick the right one. And in that case, rotation. We just specify the angular velocity, and it will automatically suggest us a rotation axis. If it's not corresponding to what you have in mind for your motion, you can, of course, change the position of the axis and its orientation. But here, in terms of rotation, it's quite simple. Automatically, it will identify what will be the rotation axis. And it will also give you a direction of rotation, because I'm the best for that, to launch a calculation and then to realize that the direction should be the opposite. So here they added it a few years ago, and it's very helpful, believe me. So this is the motion that we set here for the model. Of course, you also have full control of what will be done on the numerical side of things. But again, we don't ask you to be a black magician of CFD. I would say that in 95% of the case, standard setup will be fine. It's more about us. We will give you maybe the best options to speed up your calculation. So if your application requires maybe to tweak a little bit to faster the calculation, why not? And regarding the post-treatment, we will get all the standard results for CFD calculation, but we can also add extra results. For example, we are talking about external aero on an aircraft. So maybe you're interested about the lift. Here in this drone, we want to know what will be the amount of weight that we are able to carry with this drone. So what we need for that, we need to quantify what will be the force along the Z axis here to be able to quantify the lift. So for that, we just say, okay, I want you to output a force based on this region, the drone itself. So by the way, I could have directly rely on the existing CAD bodies, but I created the drone, one drone surface, okay? And you can also try to split a little bit your analysis. Here we have a wing. If you want to know what will be the lift contribution of each part of the wing, or maybe all the appendices of the aircraft, you can also create one region per area, and then you will get the individual force, individual lift for the different areas. So here on the drone, I want to calculate the force to get the lift. And then in the results, I will be able to quantify what will be the maximum carriage that my drone can handle. So this is for the setup. Now the only thing left to do is to mesh the model. So for the mesh, we do it in two steps. The first one, we specify here a meshing size. So let's say, for example, that I want to use something near from what he suggests me. Okay, above 1 meter cells, what it will do. So here we create an octree. An octree, it's nothing more than a visualization of what will be the cell size. You also get an estimation of the number of cells. But of course, if I use this level of refinement, if I have a look here on my drone, of course, I will lack of accuracy. I cannot catch anything with that. So once again, we can rely on region. This is also one way to make the best of these regions. Can be to apply boundary condition, can be to ask specific results, but also to refine locally the mesh. Here we have global edge length for the full domain of calculation. But I can go into this tab and tell him, okay, on the drone surface, I want something finer. Okay. I can also extend this refinement to the next level, to the next neighbors. But here, let's say that on the drone surface and on the cylinder of the motion around the propeller, maybe here I want to restrict as well and maybe go even lower. Now I will recreate this octree. This time we are talking about more elements. So if we look again at the drone itself, now we can expect something better. We are finer, we can catch not only the geometry, but also the physics happening around it. So if I make just a view here with not only the drone, but its surrounding. If I want to do a calculation of external aero, maybe I will need to refine as well on the wake side, because here, if the cells are too big, we cannot catch the gradient. Can be gradient of velocity or pressure or whatever, but I will just be able here to catch locally what's happening, but not here. So what we can do, we can also tell the software, okay, let's just show here some specific refinement level. So let's say that I'm interested, for example, about this one, this level of refinement. What I want to do is to propagate this refinement to the X direction. So what we can do, we can tell him, okay, I want to extend by a direction, X plus, Each time I click here, it expands what will be refined in the end. And when I have targeted what I was interested in, then I can tell him everything that is here on the screen. I want to refine it to a specific level. In that case, it was 8 centimeters, so level 12. Okay. So it will just refine here what I was interested in. And again, if we look this way on the side, now not only we get refinement on the craft, but also on the wake area to be sure that we can catch efficiently the physics. Okay. So during the calculation, actually, let me show you because I'm too talkative here, but let me just show you here an animation that I have made out of these results, and not this one, this one. Okay. So what we can get in terms of results, the pressure distribution on the surface of the drone. Yes. What we can do as well, we can visualize what will be the flow behavior around the craft. We can also have a look here. If we just make a pause here, what you can see here on the surface, this is what we call an oil flow. If you are a Formula One fan, if you remember at the precedent testing, they apply some kind of wax and paint on the surface of the car. And then it will follow the flow behavior. And then you get a visualization of the flow on the surface. This is exactly what you can compare it with. Yeah. So we get not only what's happening around the craft, but also on the surface of the craft. And then we can look into detail, for example, around this wing. Okay. But this is the kind of result that we can expect here for an external aero on this drone. Maybe I can also show you here what we get in terms of results since we ask for the force calculation. We can also get this force quantified. If I just open here a result file. For each single step, you will get the force calculated on the drone regarding the different direction, and in your case, the Z-axis. Just a matter of seconds, in principle. Oh, sorry for that. I should have prepared up front. Anyway, so basically you just have a text file. Yeah, okay. So this is it. In which you have quantification of the force here for the drone. Can be just for one wing and so on. You get the quantification of the force along the X, Y, and Z axis. And here you are able to check. So in that case, it was a steady calculation. You have here directly a visualization of the convergence of this force calculated. So you are able to quantify what would be the carriage that you can handle with this drone. What is the lift force? Okay, so let's come back here to the presentation. I hope you're still awake. Okay, so the demo, we just did it. Other application in which we can bring some value. Here regarding high speed flow. So the difficulty with the high speed is that it implies different physical phenomenon that maybe you want to catch, depending again on the speed of your application. If it's at low speed, okay, it's traditional CFD. But if you are going into the high speed side, then you will ask for more result and more physical phenomenon to catch. For example, shock waves. Shock waves, if you are above Mach 1, you are interested about shock waves. But shock waves on a physical perspective, that's huge gradient that you want to catch. So you have two solutions. First one, you refine everywhere because you don't know where the shock wave will occur. But of course, it's a very heavy model, very long calculation. Second solution, you use our tool, because in our tool, we are able to refine dynamically. So it's what we call the automatic mesh refinement. Locally, along the cycles that you're solving, it will refine where the gradients occur. It saves massive amount of calculation time. But if we go even further here, we're going faster and faster here. If we are at Mach 6, then you get species dissociation. Then if you go even higher, you get ablation occurring on the surface of your system. So you must use a solution that can deal with this kind of physical phenomenon. And this is what we have developed here with Dr. Nishikawa, working at the National Institute of Aerospace in the US, because not only we need fast calculation, we need accurate solution, but we need also robustness. As I said, high speed, very high gradients to consider, so you need to get a robust solution, otherwise you will always have to come back to the model, tweak some parameters, try again, and so on and so on. So you need a robust solution. This is what we have. So here, one example about a bullet that is shot again through a silencer system. Here we have been able to represent this accurately up to Mach 5, and we were 3 times faster than competition in that case, thanks to all the features that I've been explaining. Of course, if you are interested about validation model, bibliography, and so on, we have dozens of models on which these specific solvers and features have been tested, and we have looked at correlation regarding what was available in the bibliography, but what we get also in the software. So if you're interested in, again, we can provide you. One point I wanted to discuss as well, CoSimulation. In real world, you have an application that maybe implies different physics. Maybe you have a system with fluids. Maybe the system will deflect due to the fluidic force. Maybe the system will have a complex motion. So maybe your application is in between. When we go to the simulation world, this is what happens. You get one solver per physics. You get one solver for CFD, one solver for structural calculation, one solver maybe for nonlinear, so it can be both, but anyway. You can also have one solver for complex multi-body dynamics simulation. But within the MSc portfolio, we also have MSc CoSim. What CoSim does, it builds some bridges between the different solvers. It can band together the different solvers to get a coupled solution. One example, here, external aerodynamism. You have the air that is acting on the surface of a wing. Due to these forces, maybe the wing will deflect. So you can perform a CFD simulation, you send the effort to the structural code, and then you get your deflection. But this deflected wing will also alterate the CFD that is around the wing. So you need as well to come back to CFD. So you need to tell the CFD, the wing is not fully flat, maybe it's bended. And then the CFD will update its calculation. So maybe the force will be affected as well. So you have to make a coupled simulation, CFD and structural code working together. Otherwise, you won't be relevant in terms of accuracy. So here with MSc CoSim, we can not only bound 2 solvers together, but we can also bound 3 of them. I will show you some examples of that. First example here on a projectile. If you want to be sure that your projectile will aim the target you were targeting, you need to be sure that the fins will remain as it was supposed to be. Otherwise, if you have a bend in the fins, maybe you will deviate from your initial target. So that's not what you want when you send a projectile. So here, CFD code will calculate what will be the behavior of the flow around the projectile. And then, in that case, Mark solver will calculate what will be the deflection of the fins due to the speed here of the cruise. Another example between CFD and structural, nonlinearity. Here we are talking about a membrane valve. So here the fluid will push on the membrane, it will deflect here. And due to this deflection, it will also alterate what will be the flow rate of the flow passing through the valve. So here you need this strong coupling, otherwise you cannot simulate that. Another example, I was touching about that, a wing, the airflow around it, how it will bend the wing. If you are looking for fluttering phenomenon, so fluttering, you know what it is, so you have a small solicitation, and then what you expect is a kind of dumping here effect of your solicitation. You have initial solicitation, And then along the time, you want this solicitation to be dumped. This is the normal way of behaving of a system. But in some cases, what you want to avoid, it's fluttering effect. Fluttering effect, you get an initial solicitation, and then along the time, this solicitation will be amplified. That's the same story of, you know, this video of this bridge that was dancing. So this is not definitely what you were targeting in terms of application, but physics are what they are. And sometimes you get also some fluttering phenomenon. So you need to be able to anticipate them, and you need to be able to catch them through simulation. So in that case, everything is going fine. Okay, you get a first bending phenomenon, and then it's reduced a long time. In that case, it's not happening very well. You get a first oscillation, and then it goes crazy. The same phenomenon here, depending the cruise speed and altitude. When it's going well, okay, so you get a first bend and then it's attenuated along the time. When it's happening not good, you get a first oscillation and then it gets wide. So if you want to avoid this, you need again to be able to anticipate this. Another example, the rear flap of a wing. Here you get the CFD calculating all the force that will be applied to the structure. And you get also multi-body dynamics system, ADAMS, calculating the force here in the system. Not only about the motion itself of the flap, but what will be the force here in the arms. And why not adding the third joke here? So CFD for the force acting on the structure, ADAMS to drive the motion, and Nastran as well to get the deflected shape of the flap. Here, this is when we consider rigid flap. Here, this is when we consider elastic flap with deflection. As you can see here, it should not be neglected. Otherwise, you cannot expect to be accurate. The last point that I wanted to touch here, it's about aeroacoustic. What is aeroacoustic? It's noise propagation through a field. Can be air, can be water, can be liquid, or whatever, but this is what we are looking for. In that case, the CFD would be the way to calculate the boundary condition of an acoustic simulation. You calculate CFD, and then the acoustic solver will know what will be the noise generated in the system, and then the acoustic solver will anticipate how it propagates in the field. So why calculating aeroacoustic? Can be for comfort. Of course, if you have something very noisy near from you, you are not in a comfortable situation. It can be for security as well. If we are talking about defense application, if you want to create a stealth aircraft, you don't want to make too much noise, otherwise you will be spotted by the enemy. Or it can be as well for brand recognition. If you are working for Harley-Davidson or Ferrari, you want your next product to have the same sound signature than the mythic one of the brand. So can be also another purpose here for aeroacoustic simulation. As I said, we perform a CFD simulation to get the initial boundary condition to be processed in the acoustic simulation. Traditionally speaking, we need a very detailed CFD run to be able to make this kind of coupling here. So when I say very detailed, we are talking about large AD simulation, CFD simulation. So it's something quite heavy in terms of calculation time, calculation file as well. And here, the fact of working closely with acoustic teams as well, because we are in the team MSC, so our development can freely talk to each other. We have been able to develop here another approach in which, of course, we won't get all the results that we can expect from this traditional approach, but it's enough here to make some iteration exploring, let's say. So we can use just a light CFD simulation. So if you just compare here the calculation time, you can see what I'm talking about. Again, pragmatism. You make a light CFD simulation, you use it as boundary condition to get a very simple here acoustic simulation, giving you the result you were looking for. Is it better or worse than the previous iteration? If you are looking here for design iteration, that's perfect because it's not that time consuming and you will get your answer. But maybe for a validation perspective, if you want to quantify the noise exactly, maybe then you can focus on the best solution and then to make a traditional simulation. So here one example, again coupling different solution. Cradle CFD for the airflow around the rotor, Nastran to calculate the deflection here of the blade, and from that we get the CFD results. We are able to send it to Actron or acoustic solver. So not only we can bound physics together, but some application requires a lot of them. CFD that will bend the rotor, then you need the structural code to anticipate this bending, and from that you get something relevant and accurate, representative of the reality, and then you send it to aeroacoustic simulation. So I've been very talkative. I hope you are still with us. Just key takeaway, if you have to remember something about this whole presentation, I hope you have seen why Cradle CFD or product can fit your needs. We are talking about pragmatic CFD simulation. So the point for you is not to create a mesh, it's not to get result, it's to get something within the amount of time that you have at your disposal. You need to get answers so that you can make decisions. Our history, now we have more than 40 years of expertise with our customers, so it's kind of partnership with them. So we have a very wide application coverage, electronics, automotive, aeronautics, heavy machinery, different applications that we have been facing for decades. So now our solution is quite mature to address all these kind of problematics. And not only we can deal with CFD problematics, but within the MSC portfolio, we can also go beyond CFD, because CFD, that's important, but maybe your application requires more than just CFD. So that's a good point of being within a huge portfolio. All these solvers can talk to each other so that you can be sure that you will be able to accurately solve your application. And that was all on my side. So thank you very much for your time and talk to you soon.
Thank you, Max. It's much appreciated. Every time you present something, I learn something new. There's a couple of small things that was really cool to see as well. So thanks. Any questions?
If it comes after, don't worry. Just reach SimTech guys, and they will be able to answer to you as well.
I have a question. Your mesh of your impeller, was that a discontinuous mesh? The share screening happen at that time?
Yeah.
Or was that a
it was a discontinuous mesh, yeah.
Okay.
It has different names, regarding the solution that you are talking about, but yeah, the principle is that you consider boundary condition in motion within this domain, and the rest of the domain is static. Yeah.
Okay. And from once you've created your octree to creating your mesh, how do you know how fine to go off the surface of your glider in this case?
Here it's more based on experience, let's say. At the beginning, you have to. So actually, there are two ways. You can refine more than needed to be sure that you catch what you want, but we can also use what I was mentioning, the automatic mesh refinement. So it's a technique within the software. You don't have to play with the files and so on. You can directly ask for it. It means that the solver will directly run few iterations. So you can set up how many iterations it will run, but maybe, for example, 100 iteration. And then you ask him to stop, to look where the higher gradient of velocity, of pressure, so you can also weight what will be the most interest for you. And then the solver will automatically refine the mesh locally where the higher gradients occurs. And then you can do it on several iterations. I don't know if there is a limit, to be honest, but usually we make it something like 3 or 4 times, and then you get the refinement where you need it.
Okay. Is that under the mesh settings dialog?
Sorry?
Is that under the mesh settings dialog?
It's not in the mesh itself. It's more on the setup of the simulation, I think, if I remember correctly. Maybe it's in the mesh. To be honest, I don't really remember, but it's in the software.
Thank you. That's all.